So let me start with one particular possibility, which is similar to your homework problem. In your homework problem, you have two speakers that emit sound synchronously at the same time. Well, here let me consider two openings in this screen. And the light wave hits the screen with two slits. So then by Huygens principle, I should consider this slit and this slit as a bunch of point-like sources for the next wavefront. And it's that next wavefront that will hit the screen. So what do I expect to happen, for example, at this point? There will be a wave going along this line and another wave going along this line, just like in your homework problem with two speakers. The wave traveling this way comes there at the minimum, and so is the wave traveling this way. Why? Because they travel the same distances. So in the spot right in the middle, these two waves add up constructively, and that results in a stronger wave. So if I am recording the amount of light that I receive here, I'll have a maximum. What about the spot on the side here, where the difference in paths is exactly half a wavelength? Well, here, this wave comes in at a maximum, and this wave does almost as many wiggles, but has 1/2 wavelengths less to travel. So then they are mismatched by half a wavelength. And so one of them comes in like this, and another one comes in like this. They add up to nothing. So somewhere here, on the side of the maximum, I should have a minimum. What happens at the next point? At the next point, I'm going to have now one full wavelength of difference between this path and this path. And so even though this wave will have fewer wiggles than this wave along the path, they both will arrive at the same phase because this one is just shifted by one full wavelength. So again, they will arrive in the same phase, and their addition will give me a stronger wavelength. A stronger amplitude. So again, I will have a maximum, and then a minimum, a maximum, and minimum. This combination of maxima and minima produces this pattern that we see there. And this is a very beautiful demonstration of the wave properties of light, because you actually see the addition and cancellation of waves as they approach the screen. Here is a picture of this. So you can see that the two point-like sources that correspond to these two slits add up in phase or out of phase depending on where you are on the screen. And as a result, you get constructive interference, destructive interference, constructive interference, and you get light and dark spots on the screen, and that's what we just observed. Now, I used laser light which is a very nice coherent wave with the same wavelengths. What makes laser different from a flashlight is that purity of a sine wave that comes with the very well-defined wavelengths. Now, what if I use white light instead of this single sine wave of red light that has a very well-defined wavelength? If I use white light, then, of course, I measure these distances now in different wavelengths. So the spots will not coincide for the red light and the blue light and the green light. The white light contains all wavelengths. And so when I use all of these wavelengths superimposed onto each other, I'm going to get a mess. Instead of clear red dots, I will get a combination of different colored dots, which will not be as, it will not be as obvious. You can still see a rainbow at each point, but it will not be as clear a demonstration as I get with the laser light.